Hey everyone, thanks for being here. Uh, we'll probably, nope, that's not it.
Let's give it like another 2 minutes.
Hey everyone, thanks for being here on time. God. All right, I can't tell. Someone like yell or give a thumbs up if you can hear me, but I don't think that you can.
We can hear you.
Can you hear me?
Oh, you can. Okay, I can hear you now.
Okay.
I wasn't getting the little green thing on the microphone, so I don't know why. All right. Thank you, whoever spoke up. Thanks everyone for being here on time. We're gonna jam pack a lot of stuff in here, and we're for our mental health as well as yours, not run any past 9. So rather than waiting another like 5 or 10 minutes, let's just jump into things here. My name is Eli. I'm here with Zane. We are both here from the Google Developer Student Club and running the first week of Foundation exam review sessions. Just a super quick backstory on the GDSC for those of you who haven't already heard about it. We're a Google affiliated student run club at UCF. And the whole point is just to teach some practical applications of theory that you might learn in different classes and just help with anything technical. So we have a Discord. Don't use that attendance form. That's not the right thing. But you can join our Discord if you want to. You can meet people. You can make project teams. You can build projects. Play with technology. We have a lot of different opportunities throughout the semester that'll be starting back up in the spring. Definitely join our Discord if you're interested, and there will be other instructions on how to connect with us from there. All right, so you guys are all here for Foundation exam review sessions. This is week 1, so we're going to be splitting up dynamic memory allocation and then talk about linked lists, stacks, and queues, and do lots of practice problems for each one. And then next week, we'll pick back up with recursive coding, binary trees, tries, and hash tables. You certainly don't have to come to every single week. The goal is to have these recorded and uploaded to the UCF GDSC YouTube channel. So if you miss any, you're certainly welcome to go back to those. There's also recordings from previous semesters where Zane has done this exact same thing with Night Hacks and with Shep UCF. So you can also use those as reference as needed. All right, with that all being said, we're going to jump straight into things. I'm going to pass it over to Zane to start with dynamic memory allocation.
All right. Hey, what's up, everyone? My name is Zane. I'm gonna share my screen real quick. Give me 1 second. Okay, let me know if you guys can see this.
We can see it.
Yep. Okay, cool. So, all right, so I'm gonna send this link real quick in case anyone wants it, but this is a website that I made where you can pick out different topics. So that's what we're gonna use to do this. So we're gonna start off with dynamic memory allocation. And before we end up starting off, let's just do a quick intro as to what that is. So you guys know there's different types of variables, right? So we can have an int x equals 0. And this is just going to declare a number or an integer. Then there's different types of things you can do. You can do doubles, you can do all sorts of things, right? But let's say instead of just having one variable, you want to have a collection of variables or a collection of one specific type. That's where you can create an array. So let's just do an array. And let's just say 5, right? So this is kind of how you would go about declaring an array of 5 elements. You can initialize it to some values. You can also choose not to do that. But let's just say we want to have 1, 2, 3, 4, and 5. So the thing with arrays is that this name, it actually is, I guess you can say, synonymous with kind of a pointer, because this really, in memory, it doesn't point to just one value. It really is a reference or kind of like a location in memory where you have a set of 5 values, all together, or a collection where it's just you're only able to access those things at that given point in time. So just a quick rundown on how the memory would look. Let's say you have a huge block of memory on your computer, and there's a bunch of different I guess blocks that are allocated to different parts or different programs in your computer. So let's say this block is running one specific thing on your computer, but then when you allocate this array, when you write this line right here, it's going to allocate 5 blocks, right? So now, or 5, I guess, locations in memory for integers. So these are all going to be of size 4 because that's the size of an integer. And in memory, you're going to have variables like 1, 2, 3. Okay, I actually forgot 1, 5. There we go. So this is kind of what it's going to look like in memory, right? So like I had mentioned, this variable is actually pointing to the starting value or location in this array, this collection of variables that are all together. It's called contiguous. They're all together in memory. They're back to back to back. As you see, there's no, there's not an element like right here in between them. They're all consecutive or contiguous. So this is really pointing to this here. And then from there, you can go ahead and access any of these elements. So if we want to do 2, since we start with 0 indexing, this is actually referencing, or this is going to give you the value at 3. And like I had mentioned, since this array value is synonymous with kind of this location in memory where this 1 is at, if you do something like r plus 1, this is actually pointing to this box here in memory. If you do plus 3, now it jumps from this initial location 3 forward, so 1, 2, and then 3. So this is where it's actually going to be pointing to. So that's kind of the idea of it behind how it works in terms of like, what do you call it? Like different places where you're going to be referencing in memory. So dynamic memory allocation, instead of statically like saying, okay, I want this size, which right here we're defining the size, dynamic memory allocation allows you to maybe give a dynamic size. So instead of putting this 5 right here, let's say you're going to read in a variable from memory. So you would do that with something like scanf %d. And let's just have a variable. So we're going to have an int n. My bad, guys. My handwriting isn't the best in this. So int n. And let's say we're going to read in a 6. So now this variable is going to be equal to 6. So let's just write it in red. That's going to be equal to 6. And now from here, we can actually end up setting this value, or we can use this value to actually allocate something that is going to be dependent on what we actually enter. So we entered in 6. This could also have been a 5. It could have been a 20, it could have been a 30, it could have been any number that you wanted to. And from there, what we can end up doing is, instead of defining the fixed size, we can actually use different functions that there are. So there's 3 different functions that you're normally going to use. So there's realloc, there's calloc, and the one you're mostly going to use is malloc. So really what malloc does is it takes in, to make it simple, just a number or a certain size of how many things you want to allocate and kind of like what the total size in memory is going to occupy in one consecutive block. So right here, like I had mentioned, integers are they're 4 bytes. Then we're going to have 5 variables. So we can say that this total block right here is a size 20 overall in memory. So we can do, for example, size of an integer. Oh, sorry. Size of int times n. And let's just say n is equal, instead of 6, let's make it 5. So n is 5. So then we can say that this right here is going to end up creating a block in memory similar to this, but without any values. These values, like, it's not going to be really anything that you care about. It's just going to give you this block in memory right here. And like I had mentioned, it's dynamic. So we could have added in a 7, and that could have kind of, you could say, you could just extend it to 2 further values down here. And now our total block is of this size right here. So that's kind of the whole point of dynamic memory allocation. You kind of want to allocate something as you go throughout the program. Initially, you don't know what the size of what it is you're going to be doing in the program is. Like, it's not going to be fixed. So we might want 7, like I had mentioned, just different values. So that's why you would use dynamic memory allocation. And just to talk about what these different functions do. So we have malloc, and like I had mentioned, just defines a contiguous block in memory, or it could be just one. When we do calloc, it's a little different. And the way, and this one actually takes in 2 parameters. So the way I like to remember it is, it starts with a C. So calloc starts with a C. So that means the first value right here is going to be the count, the number of elements you want to your block to be of. So we can set this as n. And then here is going to be the size of each individual element. So just like we had done right here, it looks very similar to what we have in malloc, but it's going to be slightly different. Just do size of int. So this will actually kind of work the same way, but the only difference is that calloc, it takes in 2 parameters, the count and then the size of each element, and then it also initializes all the values to 0. So these are all going to be 0. With malloc, it's just going to be random values. They call it garbage. It's just values with no meaning. Here, if you specifically want to do 0 out a collection in memory, or I guess again an array, or really anything, you would use calloc, because it just kind of makes one step less. You know, you don't have to go through them all and set them to 0. Realloc works a little differently, and just to put it simply, you can kind of expand the size of this. So let's say you initially set it to a size of 7. If you want to make this slightly bigger and extend it 3 more values, you can do that with realloc. And there's some other cases with realloc, but we're just not going to go into that. And what it'll take is a pointer to this array. So let's just say we would have called it array. We declared it array initially. And then we can kind of set the size here. So that would pretty much be exactly what is in the malloc call. So this right here, we can just put it in right here. And that's kind of how realloc works. But of course, we'd want to change the n value if we're trying to expand or decrease. So that's the whole idea behind these 3 functions. But let's just hop into some questions real quick. All right, so we have this question right here. Oh yeah, and let me just introduce structs real quick, just so you guys understand how that works with memory. So let's say we have a small struct. Let's call it P, just to make it simple. And so we have int x, and let's say we have something else, a double y. There's many different ways that these structs can go. Like, you might have to allocate something inside, you might not have to, you might have a character array. There's different ways it can look. But if you wanted to declare something like a struct, it would be exactly the same kind of process. You would use malloc. So for example, malloc, if you want to do just one, size of struct P. Right, so this will declare just one. So it would just, in memory, based on whatever's inside of here, so whatever these elements are, so we have an integer and a double, it'll allocate the proper size in memory, or the proper space based on the size. So let's say, for example, it occupies this much. Then you can say that in this block, or in this struct that we have in memory now, we have space for one integer x, and then an integer, or sorry, a double y. And you can go in and access them or change them as you need. So you don't necessarily have to define it on the first try, or the first time you do this, but then you can go ahead and change those values as you need, and this will reference this location in memory, like in red. All right, so let's go into the first question. All right, so I'm going to set the timer. I'll give you guys 2 minutes to try it out for yourself, and then we're going to hop into the question. All right, so let's start it off. Okay, so it says, suppose we have an array to store all of the holiday presents we have purchased for this year. Then our array is a dynamically allocated array of structures that contains the name of each present and the price. The name of the present is a dynamically allocated string. Okay, so we can take, I guess, a note of that to support different lengths of strings. Write a function called delete present that will take the present array and free all the memory that was previously taken up. It should take 2 parameters and they give it to us right here. So present list is the array of structs, so the array of different presents that we have. And we just have to free the memory. Oh yeah, I also didn't mention what I forgot to mention free. Essentially what free is, whenever we have something in memory, so let's go back here. Let's say we allocated this red block right here in memory. If we want to kind of release it so then it can be used maybe in our own program, maybe for a different thing running in our computer, then you can just call the free function. So you can just pass in, for example, when we had allocated this array here, we could have just passed in free array, and that'll free it. That'll kind of just, remove it from memory, and now it's not in use by our program. So that's a quick reference right there, a quick explanation. All right, so we're gonna have to go through all of them. And the thing with these type of problems is we're gonna have to free stuff that's inside, that's kind of, I guess, dependent on each element in the array. So we notice here that this is dynamically allocated. So since this is dynamically allocated, we're gonna have to go in there and release the memory where this is at in wherever it is in memory, right? So we're gonna have to call the free function on this since it's not a fixed length, meaning it's not static. And then at the end, we have an array of presents that, notice here it says dynamically allocated array. So that also has to be free. And yeah, let's just see. So it says return a null pointer to the now deleted list. The array passed to the function may be pointing to null, so that case should be handled. Okay, so let's just start from the top. And definitely keep a reference for, or kind of like highlight or maybe like underline different things. When they give you these notes, it's for a reason. And when they tell you different words, dynamically allocated this, dynamically allocated that, it's important. And that's kind of why they're telling you. A lot of times the answers or the hints to the question are, in the question itself, or how you go about doing it. So first things first, let's check if it's null. So we have the struct array is called present underscore list. So if this is null, then if it's null, we don't want to do anything. We just want to return null because it's already null. So we can just return that. That means that we had nothing coming in. So we can't really iterate over nothing. Now, like I had mentioned, before we can free the whole array, we have to free what's inside of each element in this array. So we can iterate through it. And by the way, I use X, everyone. I know people use Y, or sorry, I, but I use X. So now we can go through all of them. And like I had mentioned, this is dynamic allocated. So for everything that's dynamically allocated, you're going to want to have a corresponding free. So if we have 5 elements in this array and they're all kind of like populated, that means we're going to want to free that many things that we dynamically allocate. So if we allocate 5 things, we got to free 5 things. So we're just going to free whatever is in present list of X dot, and this is going to be the present underscore name. So it's going to free that. And we don't have to free the float because this is not dynamically allocated, it's static. And then afterwards, after we freed that, we only have one last thing to free. So now we freed in everything at each element in the array, in each struct. So now we have to free the overall array itself. So we have presence underscore list. And at the end, once we freed it, it says here that we have to return null, representing that now it's deleted. So we can just return null right here. So really for this question, we don't have to do much more. That's pretty much it. So let's just make sure we had to handle the null pointer, or yeah, if it comes in null, meaning it's empty. And we have to return a null pointer at the end. And we have a dynamically allocated array. So that's presence list. So we ended up freeing that. We had dynamically allocated strings inside. So we freed those. So now we've done everything the problem asked of us. And let me just show you guys how this looks in memory for those that might not know. So that present list, let's just call it something else, right? So just make this a little larger. So let's say in memory we have this space for our present list, right? So this is our present list, and in every single one of these slots we have two things. We have the name. Let's just put like name, right? And then we have the price. So this is going to be the same case. So I'm just going to do N and P and then P. So the thing is, since the structure of kind of how this looks is, since the name is dynamically allocated, it's pointing somewhere else in memory. So what that means, this name variable could actually be pointing down here, and this is kind of where that word is stored. So let's just say, so let's say we have a string with one letter. So let's say it's like A. So we just have a string A, which actually looks like this. This is what's going to be in memory, but we got to free it first. So once we end up freeing that, what happens is, okay, let me just choose a different color. Okay, yeah. So once we free it, it's gone, right? Now it's good to use. So now this thing is pointing to nothing. It's pointing actually now to, let's reroute it. Now it's pointing to null. So I use X for null. Then the same thing, this is pointing somewhere else in memory. This one is also pointing somewhere else in memory. This one's pointing somewhere else in memory. So everywhere that we have these blocks that are kind of, they have something there, we're going to want to free them. So ultimately, we're going to end up going through all of these. We're going to free everything, right? And at the end, now that we freed everything inside that you can say like visually goes somewhere else, that's kind of dynamically allocated. Now we just have the original collection of items. Now that so you can kind of think of it, let's say we have one box. Inside of that box, we have smaller box. We got to empty out the other boxes inside before we can empty out the main box itself. So now we're going to call free on this array. And now all the things we've used in memory are gone. It's completely free. We fully pulled everything out, and now we're all good. So the box is completely empty, you can say. All right, so let's go on and check the solution. Okay, so let's see. So we check for the null pointer. That's good. And by the way, they do code a little differently. They declare in I. Some teachers do that, some teachers don't, but I like to do that, or I don't like to do that. So, okay, we check null. That's 1 point. Then we go through and iterate. We did that. We freed everything. Now we free the overall array, and then we return null. So that's all the points on this question. So that one wasn't that bad. So now let's go on to the next question. Okay, so let me see. Oh, this one. Nice. Oh, this one's actually more complicated, but okay, yeah. Let's do this one then.
Is this recursive?
Yeah. Do you think it's
Should we-
time to skip it?
I think we should skip if we're not doing recursion until a future
Right.
week.
Makes sense. Okay. Okay, this is a good question.
Can we
Alright.
do a quick digression here and just like cover all of the cases of using a dot versus an arrow
Oh,
to get
yeah.
a field for a struct? I think a lot of people are having questions about this.
Sure. Let's do that. Okay, so whenever you use a dot, pretty much it's static or it's dereferenced. So what that means is, let's go back to the example that I had here. Okay, so right here, struct P. So in this case, we have something pointing to this in memory, right? So whenever we have a pointer to a struct, so let me just write this a little better. So let's just do struct P, and then we just do our star, so we know this is a pointer. And let's just say something. It's something. Okay, so now we have something equal to this right here, right? So, oh wow, I just deleted the whole box. Okay, let's draw it back up. Okay, so when we call this, we have a pointer, or we just allocated this in memory, and now we kind of, once we allocate it, we got to know where it is. So that's where this ends up pointing to. And in the case that you have a pointer to a struct, that's where you're going to want to use the arrow. So if I wanted to change this X variable, let's just do it. So we're going to want to use an arrow. Whenever we have a pointer to a struct, we use an arrow. So something arrow X equals, let's just say 3, because it's an integer, right? So that's when you would use a arrow. Now, in the case where you don't do this, let's say you do a dot, when you would use a dot, let's say we don't have a pointer to a struct, right? So let's remove this. We have struct P something. In this case, we don't have a pointer to it. You can kind of just say, I guess, put simply, something is just this box itself. You don't have something pointing to it. That's just kind of what it is. So it gives you direct access. So whenever you have direct access, you don't have to arrow in. You can kind of think of it, okay, I have a pointer to a struct. So what is this doing? It's pointing to it, right? So whenever you do this, you're pointing to that struct, or you're accessing where it is in memory, and then you're referencing a part of it, right? So here X, or you can do Y. In the case where you have a dot, you can just think of it, okay, I'm not pointing to it, or this is not pointing to it. So it's just, the easiest way to say is that's just what it is, you know. We're not pointing to it, that's just what it is. So we just do a dot. It's just statically allocated, so we can just do dot. We have direct access to it, meaning it's not somewhere else. It's the memory is just right here. So we can do dot. Same thing with Y. You can set this to like 13.14, and that's kind of how or when you would do that. Now there's some weird edge cases. So just real quick, let's go back to the code. Okay. So just real quick, an edge case is, let's say you have this example right here, right? So let's say we didn't do indexing. So the thing with indexing is it tells you, okay, I want to go to this specific index in this array, right? But whenever you do that, it gives you local access, because you kind of, it's called dereferencing. So imagine you have a pointer somewhere, it's pointing to somewhere in memory, but now you want to get direct access to it, and you want to kind of write it shorter than you normally would if you didn't have this syntax. So you can just do these brackets, and it'll say, okay, now I have direct access to it. Now, like, you can do dot, and now you can you know, access the different things inside of it. So present name or price. Now on the flip side, let's say we wanted to write it in a different way. Now this is going to look bad, but we can do it like this. So this is exactly the same thing. Let me just get this out of here. So this is exactly equivalent to this. So what's the difference? Like, what's the difference in this? So this, remember, whenever you have the name to an array, it points to the initial point in, or the initial location of that, right? So of that array. So the first value. When you do plus X, it kind of shoots you off by however many elements you had. So let's say this is going to point to the first element, so index 0. If you want to go to the second element, you just do +1. And now this right here is going to point you to the second element. And it's still a pointer because this right here, what we're doing is we're using the pointers and we're shifting what pointer we're on. So that's why you can still do this arrow accessing. Meanwhile, right here, what it does, it kind of makes you not have to write it in this type of way. Because this, of course, just looks horrible. Another way you can also write it is this plus X. Told you guys, this can get really bad. So really, if you guys didn't know, the reason that they kind of added that arrow syntax is to prevent you to have to do something like this, because no one wants to write this. So really, just use whenever you have direct access. Once you dereference something, like in this case, when you use the indexing, that's where you do dot. If you have direct access to it, for example, right here, where you don't have to dereference it, you can use dot. In the case where you're dealing with pointers, you use the arrow. So I hope that kind of cleared that up. I know it's pretty confusing, but yeah. Okay, so we have this question here. So I'll give you guys like a minute or two just to look over it, because this timer's still running. We don't want it to run out. The answer shows.
The site could definitely use a pause feature
Yeah,
for like when
yeah.
you have to go to the bathroom. It's
sure.
amazing. There's a lot of really great things here.
Yeah, that pause button coming soon.
TM. I don't know how many questions are on the foundation exam, but
Oh,
it's
it's
usually
normally 12.
divided. It is 12. Okay. It'll be divided into 4 different parts and it's over the span of 2 hours. I know when I took it, it was online and you were supposed to use 30 minutes per section, but if you needed to use more on one section, like the next section wasn't available until the 30 minutes for the previous section had finished. But you could spend more time on the previous one and then move on. I don't know how that works in person though.
When you're in person, they just give you the packet. You can do it in whatever order you want. You don't have to like turn in one section before another. So you can start on the last question if you want in the last section, or in the middle, So that's kind of how they do it. But for the most part, typically the stuff earlier on is the easier type of question. I think it's usually what the questions that we're covering right now. So dynamic memory allocation, linked list, then what's other stacks and queues, those type of things. And then the harder stuff comes in the later section. Okay, so let's start on this question. So consider the following struct, which contains a string and its length in one nice neat package. Okay. So write a function that takes a string as an input, and creates a new smart string struct and stores a copy of that string in the word field, and the length of that string and the length member of the struct. The function should return a pointer to that new smart string struct. Use dynamic memory management as necessary. The function signature. There we go. So this is what the function is going to look like. So one thing to know real quick is the length is really going to be dependent on whatever string you put in. So this is where the whole word of dynamic memory allocation comes in. So I can give you a string hello, I can give you a string hello world, right? So it can be really anything. It can also just be H. It can be anything. So what happens with that is you're going to want to be able to handle all these different cases, and that's where dynamic memory allocation it comes in. If this was just fixed to 50, you would still have 50 individual like character slots you can put things into, but you might not use all of them. So with dynamic memory allocation, you can use as much as you need, only or the maximum that you need. You don't need to do more than what you actually need. So that's another way to kind of tell if it's going to be dynamic. Also, there's a pointer to it, so that's a big giveaway. All right, so we're given a string, and now we're going to want to do is take the length of it. So we do have access to this package called string.h, And that comes with a nice function called string length. So it'll take the length of the string. Okay, we gotta do a variable name. And now we're gonna want to create a pointer to the struct, because notice what our return type is. It's a pointer to the struct. So we're going to want to do smart string pointer. So new smart string equals malloc size of, and we're creating a smart string. So it's going to be the size of a smart string. Now that we have the length, we can access it from this pointer. Remember, we have a pointer, so now we're going to use the arrow, and we're going to set the length equal to whatever length we got from this function string length. So now we've populated the length variable. Now what we can do is actually create the copy of that string for this char star word. So how would that look? It will look like this. So smart string, we're going to arrow in, because it's a pointer to a struct word, and we're going to want to dynamically allocate. So we don't want to set it to 0. We just want kind of a blank slate. So let's use malloc size of, and we're dealing with characters. So we're going to do times or size of characters times how many elements do we have? So you would think that, okay, I have 5 letters, let's do 5. But the thing is, in C, these strings actually have this null terminator. This looks like 2 things, but it's actually represented as 1. So we have 1 extra character that we're going to want to deal with, or we're going to want to account for. So that's going to be n plus 1. So that gives us that little extra space at the end. And now we're going to want to copy the string over. So remember, in the string library, or string header, there's a function called string copy. So kind of how that works is this is the destination and this is the source. So it takes in pointers to character array. So the first character array that we have is the source. So that's meaning where we're going to copy from. And then the destination is where we want to put it. Where do we want to copy this stuff into? And that's where the new smart string word element is going to come in. So now at this point, we've malloced it. We've, okay, let me actually save this here before Mario runs out. Oh boy. Okay, let's close this up before the answer comes out. Okay, so like I was mentioning, we took the length, we've created the space in memory for just the struct itself to hold everything together. Now right here, we're going to actually give space to the word, so then we can copy it over, and we want to set the length. So now we've done those 2 things. Now we're going to copy everything over. So now we're going to copy what word was passed in. So if we were passed in hello, now in memory, in the struct, let's say this is the struct. Now we have char star word. This is going to end up pointing to, right now you can say it's nothing, but it's just kind of a space where we're going to kind of put the word that we end up copying over. Then we just set the length. So just say int length. So this is not proper syntax. I'm just kind of showing how it looks. So just equal to n. And like I had mentioned, this is going to be whatever size you set it to. And then you got to copy it over. So if we were passed in hello, now we're going to place in here hello. And now this is what we have. So they just told us to create the smart string and then just return it. I don't believe they asked us to free it. So in that case, then we're just going to return the new smart string. So I'm going to return the smart string, and that's it. That's it for this part of the question. Now for the second part, it says, now write a function that takes a smart string pointer, which might be null, as its only argument, and then frees all dynamically allocated memory associated with that struct and returns null when it's finished. Okay, so like I had mentioned, for every malloc, there has to be a corresponding free. So you made 2 mallocs, you got to make 2 frees if you want to, fully free all dynamically allocated memory. So remember, we gotta go inside first, and then we can kind of think of the outside. So remember, if we have a box and inside that box, we might have one box, we might have multiple boxes. We got to free what's inside of the box, or the boxes inside of the box before we can free the overall box itself, right? So let's just handle the, there's one case that we're gonna want to handle, I believe. So let's just say, because it says which might be null. So in the case that it's null, just like the previous question, if s equals null, that means we have nothing to free, so we can just return null, because that's what it asks us to do right here. And in the case that it's not null, then we're gonna want to go inside first. Or actually, it's called s. So s, and remember, it's a pointer to a struct. This is a struct right here, and it's a pointer. So we're gonna want to go in, and then from there is where we can reference whatever it's just called. What was it called? Oh yeah, word. So it's called word. So free the word inside, and then we only have a integer. So it's not a pointer. It wasn't dynamically allocated. So we can just end up freeing the overall struct itself. And at this point, we just have to return null. So like I mentioned, there's something in the box. Let's free whatever's in the box. Now that the box is empty, let's free the box itself. And then we just return null. So that's what's going on right here. That's what we ended up doing. And notice, we allocated the smart string. We freed the smart string. We allocated the word itself. We freed the word itself. And if you notice, kind of the way we ended up doing the mallocs and the frees, they're kind of in reverse order. So we malloc the struct itself, we malloc the word then, and then now we're going to want to free what came inside. So we're freeing the word, and then we free the struct itself. So it's kind of reversed. So yeah, just take a note of that. All right, so let's see what the answer is. Okay, so we end up, so they kind of did in a different order. I took a variable right here, but so you malloc the smart string. So we did that. Then you set the length variable. I did that right here after I took the string length. Then you malloc the word itself based on whatever the length is. So s arrow in length plus 1 is the same thing as n plus 1 right here. So we malloc that to the right size, and then we just copied the word over, and we ended up returning the struct. So that's good. We got all those points. And right here, okay, what is that? There we go. I don't know why that white space happened, but okay, so if it does not equal null, so pretty much here they're only handling the case where it's not null. So it's pretty much the same thing that I did here. They just kind of changed up the code a little bit. But in either case, we return null. So if it equals null, we return null, which happens right here. In the case that it's non-null, we're going to want to free the word and then the struct itself, and then we end up returning null at the end. So it achieves the same thing, and this gets us full point on this question. All right, so let me know if you guys want me to do one last question. Otherwise, we're going to move on to linked list where Eli's going to take over. If you guys want anything cleared up on dynamic memory allocation or anything, let me know.
Are there going to be any instances where we use Reloc or calloc, or just mostly malloc?
So it's mostly going to be malloc, but there's a couple cases where we want to use calloc. But for example, okay, let me just do it real quick. So when would you use calloc? Let's say you have a string. So really a string, let's just say hello. Or actually, let's do A, B, B, C. Okay. So right here, we have different characters. Let's just say they're all going to be lowercase. And let's say you wanted to count. We're going to be going probably until 9. So, okay, so let's say you wanted to count how many of each letter is in the string. So remember this right here says this is the end of the string. So we're just going to kind of ignore this one. So let's just not think about this one. But let's say you wanted to count how many times each letter appears in the string. So you're going to want to use what's called a frequency array. And pretty much what that does is it just keeps track of how many times something has appeared. And you kind of use the indexes to tell you. So there's 26 letters in the alphabet. So when would you use calc? If you want to create an array of integers that are all started out of 0, where initially you haven't counted anything, right? And the first index is 0, then 1, then 2, and then you end up at 25, meaning it's of size 26. So you can start off with 26 times and then comma size of int. And you can iterate through this, and there's some math involved, but A is going to end up mapping right here to this index because it's the first letter. B is going to end up mapping here. And then now when you get to this letter, you're going to increment it to 2, and then C, or actually C, you're going to mark it right here. And let's say you had another letter like F. So D, E, F, then this one will be marked up. So this is kind of a case where you want to use calc because it's just easy. It just initializes everything to 0, which you're going to want to do either way. In the case where you use malloc, you wouldn't have it all to 0, just be random values. They call it garbage. And then you would have to do a for loop and go through 26 elements to do that. But calc just does it all in one go, so you don't have to do that. Just makes it a little shorter for you. So that's one case you would use calc. In the case where you want to do reloc, is let's say you have an array of 3 elements, but you want to make it 6. So that's where you would want to kind of extend it over. That's when you would do reloc. Like I mentioned, there's some edge cases with that where you're gonna have to do some extra stuff, but for the most part, this is kind of how reloc works. And there's very few questions that are on reloc, maybe 1 or 2 across like 20 exams. Typically, they want you to not use reloc. So I wouldn't worry too much about that. It can come up, so just know the basics, but yeah, I don't expect you guys to have to use reloc. So yeah, I'm gonna pass it over to Eli, and we can get started on linked lists.
Awesome. All right, I'm going to open up a whiteboard. And we'll see if I can figure out how Zoom whiteboards work. All right, so next big topic here is linked lists, and then we'll talk a little bit about stacks and queues, which are mostly, for the most part, implemented with linked lists. But we'll talk about some other ways you can do that as well. But a linked list is kind of like the most fundamental data structure that you're going to encounter on at least part A, and generally in your work environment. It comes up very frequently. And a linked list is simply a collection of nodes, which we're going to represent here with circles. But a node is just like an individual unit that's connected to other units. And in these nodes, we might have values. Maybe we want it to be numbers, and we could represent a 3-digit number with a linked list. Or if we didn't want to use numbers, we could represent a string with a linked list here if we wanted to. We can represent lots of different types of data, but generally each node will have one piece of data inside of it and then have connections to either the node next to it in the list or to the front of it. And so we have special designations that help us access this linked list. Normally what we'll do is we'll keep access to the head of the list, which is the very first node. And maybe we'll also keep track of the tail of the list if that is useful for whatever purpose we're using. There's a lot of different ways that we can set up our linked list depending on what kind of problem we're trying to solve and what makes sense to do. So before we talk about those specific ways, there's 2 different ways that we can actually implement this. We can implement it with nodes here, and each node in the context of C would be an individual struct that we've created. So let's do that really quick. So we could call this a struct. I need to get this mouse pad out of the way because that is not helping. And we'll call this P. And inside of this struct, we can have an integer, which is a piece of data. So maybe this node is representing a 3. And then we'll also usually have a reference to the next node in here. Just realizing how incredibly slanty this is. So what would the basic way of representing this would be to have a struct, and maybe we keep track of the head. So down here we could have a reference in our code to struct p, and this would be head, and this is equal to something. We'll go ahead and set this up however we want. And if we want to go through our linked list, then we need to start at our head and just call head arrow, since this is a pointer, and get the next element. And then if we get the next element, now we have a reference to our 0 here, and then we could get next again and reference our tail. So this is one way of doing it. We could use structs. Or the other way that we could do this is we can create everything in one piece of data here. So let's call this Q. And we can represent a linked list as an array as well. So our linked list, or it's not a linked list at this point, but this is another way of representing a list. We could have our array, and we can have a bunch of different elements in here. And we could have maybe a 1, 2, 7, 3, 4. And we might also have a counter of how many things are currently in here. So our count right now would be equal to 5. And we could put all of this data together in a struct. So we could have our array here, and then we could have our count here. And this will be really useful once we get back to our stack and queue implementations a little bit later, which are primarily done with a linked list, but you could also use this struct here where we put everything in an array. And we'll talk about ways of doing that as we get a little bit further. Okay, so we have a couple of variations of linked lists here. So this is our basic linked list. We have a reference to the head. We may or may not have a reference to the tail that we store in our data. But we will be able to go to the next element by calling next, and so on and so forth. The other ways that we could do this, if we have, again, 3 elements here, we could have a doubly linked list, which means that they point in both directions. So if this is 1, 2, 3, we can go either to the previous one or to the next one, no problem. And if we put a struct in here, previously we only held a reference to next, but we could also put a reference in here to previous. And that way we can go both directions. So this is a doubly linked list. There's also such a thing as a circularly linked list. So if we wanted to be able to quickly go back to the start of the list, no problem. We can link our tail and our head together so that when we call next from our tail, in a list like this, if we called next, next doesn't point to anything. This would be null. And similarly here, if we got our head and we called previous, this should also be null, which it indicates to us that we've hit the end of our list. But in this case, if we go to our tail element and call next, it's going to send us back to our head element. So if you need that functionality in the list that you're using to solve a problem, or in the case of the foundation exam, if they just give you a circularly linked list, then you definitely want to be aware of the fact that if you call next on the tail, it will not be null. And so you can't be looking for that. Whereas in this case, if you wanted to figure out when have I gotten to the end of my list, well, when we eventually call node.next, or not .next, with the arrow, if it's null, then that means we've gotten to the end of our list and we can go ahead and do whatever we want. Okay, so these are the variations of linked lists. Most commonly, you'll just use a singularly linked list and you'll have a reference to the head. And problems that you try and solve will make you go through the linked list in one pass, which means you can't go through multiple times. Maybe 2 times is fine, but you don't want to go through if we say that n is equal to 3 here, where n is the amount of elements in our list, If we had an algorithm, this is kind of jumping ahead to things, but if we had an algorithm that ran in O sub n squared time, then that means we would be going through our n elements n times. And that would be very bad if you had a really long linked list. So a lot of problems you try and solve will have you go through in linear time, which means you can go through the whole linked list, but it needs to be a fixed number of times. It needs to be a constant number of times, which is usually 1, maybe 2, things like that. Okay, so what kind of problems might we come across with a linked list? Just really quick before we start to solve some actual problems. This is kind of like thinking ahead to how these are like practically useful more than it is to like, being useful to the foundation exam. But like once you get into later classes, you start doing leak code problems to practice for interviews, some of these techniques will come up. But one thing that we might want to do with our linked list is we might want to reverse it. So right now, this is our head element here. And if we just put a bunch of random numbers in here, then let's say this represents the number 32,817. Well, if we wanted to reverse this list so that instead all of our arrows were pointing the other way, and now our head element is over here, well, now this number is very different. It's 71,823. So that's something that will come up every once in a while. Sometimes you need to change the ordering of the links. Another thing you might want to do is you might want to add an element to the linked list. So maybe we want to add the node 5 in here, and we want to put it in between. We want to put it right in here. Well, now what we need to do is we need to safely unlink these two nodes and then rearrange the links so that we still have one linear thing. And so the technicalities of this get a little bit challenging. This is something you will find on the foundation exam, something similar to this, changing around the links. This is very common. So we'll do some practice problems with that. And then another thing that comes up every once in a while is a technique called the two-pointer approach. So let's say for some reason we needed to get halfway through our linked list. Maybe we want to do something to the first half and something different to the second half. Well, the hard way of doing this is going through and counting how many nodes we go through. So starting from the head, we count 1, 2, 3, 4, 5, 6 nodes. And then we start over at the head and we go half of that. So 1, 2, 3, now we're at the halfway point. One way that we could do this a little bit faster is by keeping track of two different pointers here. So let's call this P1 and P2. And we can move them at different speeds. So let's say every single iteration, we try and move P2 twice, and then we try and move P1 only one time. So after time is equal to 1, now P1 is referencing this node over here that has a value of 2, and P2 is now referencing this value of 8. And then after time 2, P1 moves once again, and it's referencing 8, but P2 is now over here referencing 7. And if we went to time is equal to 3, we would no longer be able to move P2 twice. And so we could just bump it up one time so that we know it's at the end. And now we have a pointer that's halfway and a pointer that's the other way. So sometimes there'll be problems where maybe you want two sides of the linked list to converge. So like this side would converge in here and this side would converge in here. So we could unlink these and link these together like so. And this would, one problem that I've come across on LeetCode that does this is the problem of trying to find a palindrome in a linked list. So now that we have, if we had a palindrome, this would be 3 to 8, and this would be 3 to 8. And now that we have a reference, P2 is at the tail of this list. And our front of our list is facing one direction, the back of our list is facing the other. Well, now we can grab, we can reset P1 to be at the front here. And then we can check P1 and P2 at the same time. Do they have the same value? If so, then move them forwards and move them forwards, stuff like that. You should be able to use the scroll wheel.
You can right click, you can also zoom out as well. So
Yeah.
if you right click, you can move around.
Right click. Okay, so that's shortcut for the panning tool. Sorry, I'm just kind of using the whole whiteboard since it gives me a lot of space here. Okay, so let's go and do some problems here. I want to do one problem that's coding so that we can get like the technical element of managing links, but also do one problem that's not coding, because there are a lot of foundation exam problems that either will give you code and you have to trace it out and figure out what it does, or they'll give you like, a piece of code and try and have you find, what the bugs are. And so there are lots of problems other than just writing C code. So I want to make sure we get at least some of that while we're here. Okay, so I'm going to close the whiteboard here, and we'll go ahead and do everything else in the console here as much as possible. Is it going to let me make this smaller? It is not. Oh, it is. Maybe. I just have to click it. Okay, so as we're on this site, one thing just, for reference is if you go up into the settings section, we can choose which topics we want to go for. Right now, we're just going to choose linked lists here, but if there's something specific you want to practice, you can just select problems from that category. And now we have the thing, and we could click start to start our 10-minute timer, but we're not going to do that quite yet. This is a recursive function, so we're going to skip that. We'll do recursive later. Let's go to a different one. This is also recursive, so we're going to skip that.
A lot of linked list problems are recursive. Oh, this one's.
Yes. All right, we're going to do this one just because I think it's fun, and we're gonna go ahead and do it. It doesn't involve messing with the links at all, so probably do a different problem that involves messing with the links. But let's go ahead and run through this. So we're writing a function that gets the mode of our list. So we get a reference to the front of a linked list storing integers, and we need to return the mode, which is the number that occurs the most times. All of the integers are between 0 and 999, so it's giving us bounds, which means we don't have to like worry about a number being enormous, which will help us very shortly. If there is more than one mode, we need to return the smallest of all of the modes. So if we have the number 7, which occurs 3 times, and the number 8, which occurs 3 times, and those, nothing occurs more than 3 times, then we would run and return 7 over 8. And then stuff at the bottom, declaring an auxiliary array. We'll talk about what that means in a second. And you can assume the list pointing to the front is non-empty, which means not necessarily that this is not going to be null, which is true. If it's not empty, then there must be at least one thing in here, and so it's not going to be null. But what it means is if this were empty, then what is the mode if there's nothing in there? So it's just normally they'll give you information that handles like edge cases that like you just really shouldn't have to worry about or like question, what does this mean? So we'll note in here that it gives us a definition of a constant, max. So I'm going to go ahead and put that in our code here. So we can use this constant anywhere we want. And it'll also give us a definition for our node. So anytime you have a linked list problem, a queue problem, or a stack problem, they will give you the definition, if you need it, of the like struct that represents a node in your linked list. So in this case, we have one field, which is the value, so the number inside of the node. And then again, we have a pointer to the next node in our linked list. One other thing that I don't know if it got mentioned previously, so I'm going to mention it really quick. There is a difference between writing struct node, blah, 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 and struct, or rather type def struct node, blah, 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 node. So in the first case, anytime we use this struct in code, we will have to put the struct keyword in front of it. Something is equal to blah, 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 which gets really cumbersome after a while. So what we can do instead is we can use a type def keyword, which will rename this thing to be this name that we put afterwards. And so now anywhere in our code, as you'll notice down here where it's giving us a parameter, all we have to do is write node. So if we have the type def, then we're allowed to just use the node, name of the struct and the pointer star. And we don't have to put struct in front. But if you do get a definition that doesn't have type def, which they do fairly often, in that case, you will still have to put struct in front of it. And if you don't, you could potentially lose points for it. So that's something you should definitely go back and look for every time you solve a problem. Okay, I'm going to put this definition into our code. We're just going to paste it directly. And we'll go ahead and put some tabs in here. And let's go ahead and think about what we need to do here. So we need to find a way of how many times each number occurs in here. So one really naive way of doing this would be to go through this list and count how many zeros there are, and then go through the list and count how many ones there are and how many twos there are. And that would take us 1,000 loops through our linked list, which could potentially be who knows how long. And that would be very, very, very slow. So this hint of an auxiliary array, which means that we can use an array in here to help speed things up. Generally, for a lot of problems where you're trying to find the frequency of something occurring, what we can do is we can find frequency is equal to integer array. And let's set this to be the length of max. I think, forget the syntax here. I think this is it. Zane, you keep backing me up on this. Which direction? I think data types.
Yeah, that should be good.
This is it. Okay. So in this case, we're creating an array of length max since it gives us the constant. And now what we can do is in every single slot of this array, we can increment it 1 every time we find a node with the value of that index. So if we find a node with a value 3, then we take the third index of frequency and we increment it by 1. And that way we only have to make 1 pass through our linked list. And that saves us 999 passes, which is very, very, very good as a space modifier. So let's go ahead and do that. So our list is non-empty. So let's make our pass through here, since this is the easy part, or the easier part.
You gotta
So let's write
initialize it to 0. Like every value.
Right. You're absolutely correct. So in this case, if we create a variable like this, it has all garbage values inside of it. So who knows what the number is? It might be something non-valid. And so if we create an array like this, we need to make sure that we go through for each index and set frequency of that index is equal to 0. So all of our counts start at 0. If we were dynamically allocating something, we could use calloc, and calloc would put a 0 everywhere for us. But we're not dynamically allocating. All right, so we've done this. And so now we need to go through our linked list and get the value of everything we have. So we can do that with a while loop. And we're going to go while our front is not equal to null. So our front is a pointer to a node, and we are basically assuming here that it's not going to be null initially because the list is not empty. But if we didn't know that, we would want to first check, or it wouldn't even matter in this case. But while front is not null, we're going to take the value of front and we're going to stick it into frequency front value, and we're going to increment it by 1. So because it's a pointer, we have to use our arrow here. We're going to get the value. We're going to index frequency, and we're going to increment it by 1 with the double plus sign operator. And now what we need to do is we need to go to the next node, because if we stick on the same node, it's going to be an infinite loop. And so what we can do is we can say front is equal to front arrow next. And so this gets a pointer to the next node in our list, and then we reassign it into front. We don't need whatever is currently in front. We're not going to go back through the nodes again, and so we can break this. We wouldn't have any way to go back to the head of our list if we needed to, because we're changing the value of front. If we wanted to, we could put a variable here to keep track of our head, but we don't need to do that here. Okay, so now our frequency array is complete. And so what we can do here, could you also do int freq max is equal to 0? I don't think this syntax is valid. if you are just declaring an array like this, you can't initialize it to anything. You need to go through and set everything to 0. It's this or callicate, which you could also do no problem.
I think that actually works, but I'm
It
not
does?
100% sure.
I've
Yeah,
never
I
seen
think
that
so.
before.
It might, but just try to do it the easiest way where anyone can recognize it, because there's many different TAs or people, grading you. So you don't want to like do something that most people can't recognize or may not recognize, because they might take points off, so just do it like the simpler way.
So it'd be a good experiment to do on a replit or something. Okay, so now that we have our frequency array incremented, we need to go through and figure out what the highest value is. And we want to return whatever the index that has that, which is the lowest index. So if there's multiple indexes with the same mode, then we return that. So what we can do is we can keep track of the index, and we'll set this to be -1 by default, and mode is equal to 0. Actually, we'll set this to 0. And what we can do is we can check if frequency of I is greater than mode. And in that case, we want to update mode to be frequency I and index to be I. So if we find something that occurs more times than whatever our current max is, then we update it. Note, this is not greater than or equal to. If it were greater than or equal to, every time we find a higher index that has the same value, it would update it to use that higher index, but we want to use the smallest index. So the first one we come across is the one we're keeping. And then at the end here, what we need to return is an int. And we are returning the mode, not the index. Or no, we are returning the index. We're returning the thing that occurs the most times. We don't care how many times it occurs. Okay, so let's go back and make sure we solved all the problem. We have our frequency array here. We set it all to 0. While we still have nodes in our linked list, we're going to take the value of what we currently have and increment the frequency array. We're going to go to the next one until we get to the end. Once we get to the end, front.next, if we have our linked list, the last thing front.next will be null. And so now front will be null and the while loop will break. And then for each thing, we just update the mode if it's bigger. Okay, so theoretically we've solved this one. Let's go through and see what I managed to screw up this time. So they have their frequency array, set everything to 0. While the front is not null, they increment frequency and then go to the next one. So we got all that right. And so they're not keeping it as 2 variables. They're just keeping the index where the previous mode happened and then re-indexing frequency. So either way works here. And then we return our index. Okay, so we would have everything here. If we initialized our frequency array, but maybe didn't set it to 0, they would probably take a point off because it wouldn't work, or 2 points or even 3 points. If ties were broken incorrectly, which means, if we had done greater than or equal to here, so it would take the biggest index, we'd lose another point. So you do get a lot of partial credit here, which, definitely helps out a lot. It's not make or break.
If you would have done calc, they would have probably taken points off if you did it free. So yeah, that's another thing.
Also
you
true.
Might not say it there. That might be a case.
Yep. This is the general guideline, but there are people do things all over the place. So it's not all inclusive. Okay, this is a good one. This is a trace problem. So, so this problem, we're not writing any code. We're just asking if we call this function it gives us on the list to show what the list looks like after the function is finished. So we're going to go ahead and go through this code. We have our definition of our linked list here, and we have a function that takes in the head, and it does all these things. It doesn't tell us what it does. That's for us to figure out. So usually once you get through some of these problems, like maybe halfway, you'll start to realize like, hey, this is what it's trying to do. And then that'll help you validate at the end if you have the right result. Okay, so we have our head here. So right now our list looks like head, 1, 2, 3, 4, 5, 6, 7. And so the first line here will take the reference to our head and put it into current, which is probably means that it's going to iterate through the list. And then we're creating pointers to two other nodes that currently are not being used. So right now, our current is here over the head. So we'll just put a C. This is easier if you write it out than trying to type it out. So if current is equal to null, then we'll return the head. So if the head is equal to null, in this case, it is not. So we don't have to worry about that. And now we say other is equal to current.next. So this is current, and this is other. I'm gonna get rid of this head here. I don't think this visual is good. Head is basically over the 1 here, and current is on head. And then other is current.next. So other is over 2. If other is null, then we return head. We don't have to do that. If other, okay, so other is equal to other.next. So that means other is moving over here. Temp is equal to current.next. So current.next is 2. So this is now temp. Current next is equal to other next. This is gonna be hard to visualize. Essentially, what this is saying is current is now pointing its next all the way over here, and that breaks this link. So this is no longer linked here, and rather it's linked all the way to 4. Current is equal to other next. So other next is here. So this means current is also now on this node. And this is dangerous. So we just changed current to now be over this 4. And it's also pointing to itself at 4 here. Is that true? So current next. I messed up here. So let's take this back. So current next is equal to other next. So 1 is now pointing down here to 4. A little bit of computer science ingenuity here. So 1 is now pointing to 4, and this link is broken. And now we're going to update current to be exactly what it was pointing to, other next. So current is now referencing this 4 here. If current is null, is current null? No. So we skip everything in here. Other next is equal to current next. So 3. We're breaking this link, so it no longer points here. And other next is now pointing to whatever current next is, and current next is equal to 5. So this goes over here. All right, and then current next is equal to temp. I'm gonna do this just so you remember which direction it's going. All right, so this is really complicated, and this would be better if you just drew some arrows out here. But current, next, So this is a broken link. But current next is now pointing to this over here. So if we follow this, our new list here starts at 1 still. Their head hasn't moved. And then it points to 4. And 4 points to 2. And 2 points to 3. And 3 points to 5. And 5 points to 6. And 6 points to 7. So what did this do? This just pushed 4 up a couple of spaces here, which is not super useful. Sometimes you'll get a trace problem. It'll be like a concrete thing that it's trying to do. But in this case, it seems relatively random. And our head is still over here. So let's check this and see if we got something right here. So our solution is now 1, 4, 2, 3, 5, 6, 7, which is great. And again, we'll get partial credits if we, update some things correctly, but not everything. Okay, these trace problems are really tricky. If you do a trace problem like this, go through it at least twice, like, maybe 3 times if you have time for it, but at least twice because you could always screw something up the first time, which is exactly what we did. So head is just a pointer and it just points to this node. And we assign other pointers to also point to the same node, current and other and temp at various times. And those, these variable pointers here, they just swap which nodes they're pointing to. And through that, we're changing around the links so that we figure out, so that our list takes a different shape here. Okay, definitely practice a couple of these. There are trace problems for linked lists most commonly, but there are trace problems for other code as well. Like you'll have recursive trace problems. You'll have things that do computations that are trace problems. It is a big part of the exam and you will find some. Okay, 823. I think we should move on to stacks and queues and do one problem of each. And then if we have any time at the end, we can just open for some questions. Does that work for you, Zane?
Yeah, that does work.
Okay, in that case, I'm going to pass it over to you for stacks.
All right. Okay, so let's go ahead with stacks. Okay, so this one right here. Oh yeah, actually, let me go ahead and explain the stack first. Okay, so there's different ways where you might want to store values, or you might want to prioritize a value that came at a certain time before another. So let's say, for example, you have a stack of plates and you're in a kitchen, right? So normally you don't take out this plate or this one. You usually start from the top. So you're going to take this one on and then, you're going to clean it, whatever. But now the whole point is it's off of what you call a stack. So it's a stack of plates. So you're going to end up removing this. And similarly, we can have, instead of plates, we can really represent anything. So let's say we want to have different values. So we added a collection of values and then we want the latest one that we added on. So when it comes to stacks, we follow this, I think abbreviation, or I guess acronym is the word for it, but last in, first out. So the last thing that you ended up adding is going to be the first thing that you end up removing. So in the case of a stack of plates, or in this stack of values, when we want to remove something, we're going to have access to the thing at the very top, meaning 4, and then we can just remove that. And we can kind of, place this somewhere else. So yeah, we can, okay, well, we can place it somewhere else, right? And then we can do whatever we want with it. And then now we have the next thing that came right before. So in this order, we're going to be able to kind of solve many different problems that can come up where you kind of care about what was the latest thing that I have, because you might be comparing against something else, and that information might be relevant as you go through maybe a set of values, or an array, or whatever it is that you're doing. So that's kind of how a stack works. There's really few operations. So I showed you guys push, where you're going to add something on. So let's say we wanted to add on 5. Now this is at the top of the stack. And we also have pop, which I showed when we removed 4 and put it right here. So it's push pop. There's also another one real quick, that's peak. So in this case, peak, we have a stack of plates and we want to peek and see kind of what's at the top, we can get kind of a quick reference to what it is. So if we peek on this stack that we have right here, we're going to see, okay, we have a 5 at the top. If we remove this, we're going to say, okay, we have a 2, a 3, and then if we do it again, now we have a 2, and in this case we have a 1. So that's just kind of how that works. There's also another case or another function that we might have where it just checks if it's empty, and it's kind of self-explanatory. If the size is 0 or maybe a pointer is null, in that case, you know, a stack might be empty. So there's different representations. In the case of an array, you can, let's say you add on a value 3, then this is going to be the top of the stack. Then you can, if you want to add, let's say a 5, then now this is the top. If you want to remove, you move this back 1. And even though there's values here, it's going to end up, even though the value's there, it's going to end up being rewritten. So let's say you want to add on a 6, then now your top is going to be here, but now you're going to just overwrite this value. So now you have a 6, and then you can add on a 7 and remove it, etc. But that's kind of the whole idea with an array. When you have a linked list implementation of a stack, let's say we have a set of values in an array, 1, 2, 3. We're going to add on 1, and this is going to be the front of the linked list. And then if we want to add on a stack, then we could just make a node and link it to the front, and now make this our new front. And we can do that for the last value as well. So notice, and now this is going to be our front. So notice how the last thing in is going to be quote unquote first thing out. If you remove this, you're just going to advance front over here, and now you can keep going like that. That's it. So let's get started with the question. This one actually kind of has to do with another problem called Towers of Hanoi. So I'm just going to skip this one. And these types of problems, we're not going to go into them. We want to go on to the coding questions. So, okay, this is a good question. Okay, so I'm not going to do 2 minutes, so you guys can try it out just because we're on a kind of a time crunch, but let's just hop into it. So a word is considered a palindrome if the reverse of the word is the same as the original. For example, the word test is not a palindrome as its reverse, T set, is not the same as test. On the other hand, race car is a palindrome because if you reverse it, then it's still race car. Some other examples are Hannah. So if you reverse Hannah, you still have Hannah. Level, you still have level, and so on. So write a function that takes a string. Write a function that will take a string in the parameter and return 1 if the string is a palindrome. Otherwise, return 0. You have to use stack operations during this process. So credit is not awarded for correctly solving it, but utilizing a stack. So we have to use a stack. You can do it without using a stack, but they just want you to use a stack. And let's see, assume the stack definition and the functions that are available to you. It will automatically be extended if it's full, so you don't have to worry about that. And the top of the stack is controlled by push and pop operations. So pretty much this is kind of called black boxing, where you don't really care how it's implemented. You just know that this is what you can do and this will work. So we don't have to worry about, you know, the technicals of how this and this function work. Just assume it does work. And here it tells you, you know, what it returns and so on. You also see the return type. So we can initialize it. So I'll set everything up, push, add something on, pop, peek, see what's at the top, and check if it's empty. So whenever we have a palindrome, let's just erase this here. Let's zoom in a little bit. So when we have a palindrome, let's do an example. So let's do level. So let me space this out as well. So in this case, let's have and I and then we can have a j. Okay, so if we wanted to do this normally, we would kind of go through and compare each character. So we start on the left, we start on the right, and we just compare. Okay, is what's at I and what's at j, are they the same? If so, keep going. In this case, they are the same, so keep going. In this case, they are the same, so we can keep going. And if you think about it, once you hit the case where they're the same, or maybe they have crossed over, meaning, so at this point, if we keep going, we would see E, and then we keep going, see E. Once we've crossed over, we don't have to keep looking because, you know, you've already kind of gone through the whole string or list at that point. So we could just kind of stop there, but we verified, okay, there was no discrepancy from the left and the rightmost value at every given point. So then we have a palindrome. Now, if we're doing a stack, let's just kind of think of how we can do that. So let's just kind of do, I guess, a array implementation kind of a stack just for demonstration. So we can add on an E or an L. We can add on an E, a B, B, and a L, right? So this is going to be what the stack is going to look like. And just know that this value, remember, last in, first out. So this is really at the top. This is second to the top, third to the top, etc. This is at the bottom. So if we kind of wanted to see, or if this is a palindrome using a stack, if we can take note that, okay, whatever is at the top is the last value. So really, in this I and J example, this is our I and this is our J. You can say that since this is last in, first out, that this value right here is kind of representative of J. And this value right here, at the start of the actual string, is representative of I. So why is that relevant? We can kind of simulate the same process. Instead of moving a J pointer, we can actually pop things off the stack. So in the case that, let's just remove this right here. So in the case that I, whatever's at I, once we've added everything onto the stack, if they're the same, we can move this one forward and then we can end up popping L off. So now we can kind of say, okay, now the next thing at the top, just call this top, is E. Okay, does that match what's at I? It does. So let's just move down one and let's move this one forward. Same thing here. Pick the same. So now we can kind of keep on going. I know I had mentioned that you can kind of stop once you're at the middle point, but let's just keep going. And, you know, we see there's another match. And we're going to see one final match. Okay, they match. Good. And now we've gone through the whole string. In the case that we get through it and we find a match at every given point, then we know that we have a palindrome. We don't have to keep going any further. So that's kind of how we can think about it using a stack. We're not necessarily keeping a J pointer, but the stack structure kind of simulates that process. So let's go ahead and dive into the question. Okay, so they give us a struct stack. So they, unfortunately, they didn't type diffs. We're gonna have to write struct stack. Or actually, we don't have to do that anywhere else. But okay, so we have the length of the string, and now this indentation is really bad. Okay, there we go. So it's been initialized. So now we don't have to set anything up. Now what we're gonna want to do is populate the stack. So how's that gonna work? We can just iterate through every element in the string. So we have the len right here, the length. So now we're just iterating through everything in the string. And we can just push things on. So how do we do that? So it says push, so stack pointer S and then character value. So the thing is, since this is a pointer and we have this statically allocated, note how they did an ampersand. This gives us a pointer to this in memory. So we can just, I guess, kind of turn it into a pointer for this function or give a reference to it right here by doing the ampersand. So that gives us the address. And now we can just add on whatever character we're currently at based on the index. So in the example of level, at 0, we're going to be at L. At 1, we're going to be at E, and so on. So we're just going to add on string of X. So now at this point, we have in the stack, like I had mentioned, we have level. And at the top, we have what technically is the J pointer. So it's at the very end. So whatever's at the very end is now at the top of the stack. So how can we check whether or not this is a palindrome? We can end up doing a while loop to kind of empty out the stack. And whenever we end up hitting the end of the stack, meaning there's nothing else to go off of, then at that point, we're going to know, okay, we're good. But that's because we're going to handle any cases where there's a mismatch. So what's our condition? We're going to want to go through every character in the stack and empty it out. So we're going to have is empty and ampersand s. So we're going to want to go while is empty is false. So in the case that we're not empty, we're going to want to keep going. So this right here just kind of, if it is kind of negates it, so that turns it like if it's not empty, we're going to say, okay, let's keep going. Okay, so while it's not empty, then we're going to want to check. So we're going to pop off whatever's at the top. So remember with our example, let's just write it out right here. We have level, and then in our stack, we have this right here. So now this is what's going to be at the top. We're going to want to pop it off. So that's going to look like character top char. And we can do pop of ampersand s. So this gives us the top character. And we can check. Oh yeah, also let me track the index so we can have an index variable as well. So at this point we can check, okay, does what's at this index match what's at the top? So if s of index, or actually it was str of index does not equal what's at the top, in that case we know that we don't want to keep going because we found a mismatch. It's not a palindrome. So for example, if this was an X and this is an L, then we know that we have a mismatch because the top character does not match what's right here on the left side. So in that case, we want to just return 0. Otherwise, we can keep going because, you know, it's a match. It's not a mismatch. And the only thing we're going to have to do is increment the index. So that's going to make us go from, remember, we were kind of using this. So we had an I variable, and technically we can say this is our J. So we say, okay, they match. So now let's move it down a little bit. Okay, so now let's check if these match and so on. So that's kind of what we're going to want to do. But since really we're not moving J, like we're not using a J variable, we're just using the top. The only thing we're going to have to move is L. We're not deleting anything. We're just moving it up further, and popping does the same thing. So now at the very end, if we end up going through this and we say it's empty, the only way that's possible is if everything is kind of mirrored. So if they were exactly identical. So in that case, we can just return 1. So that tells us, okay, we went through it. We checked at every given point from left to right, going inwards. If they were a match, if it was a mismatch, we return 0. Otherwise, we just end up returning 1. There is no mismatch at any given point. So yeah, that's pretty much the solution for this question. You also could have used peak if you wanted to. You can do a peak and then a pop, but this also ends up working out. So let's just check solution. And I'm pretty sure, yeah. So this is one of those ones where they kind of use some math to make it a little more efficient. But trust me, it works exactly the same. You don't have to do you don't have to think through all this and try to figure it out when you're in the exam. Just remember, when they make these solutions and you know they're doing divided by 2, even though it might make sense, when you're in an exam and you're not a professor, it's hard to come up with something that's, you know, as efficient, or it goes through less iterations of this. So You know, if you're seeing this and you don't get it, you know, it makes sense. But this is not the only thing that will get you points. So let's just see what they ended up doing. So they ended up going through half of the string. So just real quick, they ended up going just up until this point, and then they ended up checking later on, okay, is the lesser half, does it match kind of what's, or actually, so right here, does the lesser half match what is from here onwards? So they just check, okay, does this match? Does this match? Okay, that's good. So they just kind of cut out some parts of the iterations. You don't have to do as much, but this still ends up working. We added everything on. We checked if the reverse at every point is the same. If it's not, return 0, otherwise return 1. So that is this question. And yeah, trust me, with this type of approach, you'll get full points as well, even though it's not as efficient.
The grading criteria on this is messy, but if you go
Yeah.
through and look, like, it's just asking, like, did they pop the right number of things? Like, did they, do it properly? So even if you do it differently and don't use the length divided by 2, they'll still give you all the points for it.
Yep, exactly. So we're actually running pretty short on time, so I'm gonna pass it over to Eli so we can do a Q question, just so we can cover at least one. But I hope this gave a good preview, or problem solving with a stack.
Definitely. There's lots and lots of different types of stack questions, so I would highly recommend going through for stacks and queues in particular, just so you can get the whole variety rather than just like the one problem where you write code.
Right.
And like someone was saying, infix and postfix, that is a stack question that you very well might see. So definitely a good idea to practice.
Yeah, just like this one. This is something you might have to do. So it's gonna be completely different. So yeah, just go ahead and practice it. I'm gonna pass it over.
All right. In the home stretch. All right, so really quick, so our stack in the past, our stack was essentially every time you have a new node, you just put it on top, and then you can take something off, and you just keep track of the top of the stack at any given time. So this is your top over here. Like Zane was saying, this is last in, first out, whereas a queue, on the other hand, is first in, first out. So a queue visually makes more sense to lay it out sideways. And our queue has a front, which is where we take everything off. So we take something off the front. Sorry, that should not be the front. This should be the front over here. And this is our tail or our back. We'll do B just to make it more clear. And anytime we put something onto the queue, if we enqueue it, ENQ, then we want to put it on the back and update our back pointer to be the new end of the list. And if we take something off, we want to take it off from the front and update our front to be the new end of the list. And so the direction of the links here is really important, because if we want to take something out the front, well, we have to figure out how do we, in constant time, update our front pointer to be the next thing. And so it needs to always point to the second element, and the second element points to the third, and so on and so forth. And similarly, if we add something to the back, we need to be able to immediately update our back pointer to the next thing. So direction here is important. This is the way that we can represent it as a linked list. So these are all nodes. Maybe this one has a 3, this one has a 2, this one has a 7, this one has an 8, just arbitrarily. But additionally, we could do this another way too. Why is this whiteboard different than the last one I used? That doesn't make any sense. All right, but we could also do this a different way here. So we could also represent this as an array. And there are some questions on the foundation exam where you have to represent it as both. Usually it'll be a linked list of nodes, but it also could be an array. So let's say we have a fixed length array here. They probably won't ask you to have a dynamically sized array because that's too many things in one question. But we could have a queue where this is the front over here, 2, 3, 7, 8, and this is our back. And so anytime that we add to our queue, we of course want to put it on the end of our array here. So if we wanted to add another 3, we would update our back pointer to say, now we're indexing index 4 in the array. And if we wanted to take something out, well, we just go ahead and remove it from the array. So this here would become now, it could be an index 0, or you don't even really have to take it out anyway. All you have to do is change our front pointer to now index number 1 here. And so now we know that our Q is directly between these 4 elements. And this doesn't play any part, this doesn't play any part. And again, we can add again to our back here. And we can move our front, so on and so forth. So now these 2 elements here are not in use. And eventually we'll run out of space here. And so, we can either reallocate space and make our array longer, but eventually, we're going to have a shit ton of indexes in the front here. Oop, I shouldn't say that. We're going to have a lot of indexes in the front that are going to be unused, and we're going to be wasting a lot of space. And so typically what people will do instead is make the array circular in a sense. And so once we run out of space at the end to move our pointers, well, now we're going to move our pointer up to the front here, and let's, we could now officially put in our new value here of 9 or so. And so now our Q goes 1, 2, 3, 4, 5. And this is not being used. And this is not being used as well. And eventually, we could have a queue that is full. And if our queue is full, we would not want to add anything else because we don't want the back pointer and the front pointer to reference the same thing. In that case, we would just not let something happen. But this is another way to represent a queue. There are some questions like this, so definitely do some practice with that. So these are 2 different implementations. The other thing I want to talk about really quick is the concept of a priority queue. This is probably not something that you'll really see until we get to heaps, because the way to do this in an array is not very efficient. There's a much better way of doing it as a heap, which is generally how they're implemented. Like if you go to Java, a priority queue is a class that you don't have to implement, but they do it underlying with a heap. So let's say we had a queue of nodes here. A priority queue would mean that there's some sort of underlying priority which puts nodes at a specific location. So let's say our priority was the smallest node comes first. And so this is our front and this is our back. Well, if we had the values 3, 7, and 1, then 1 would come first and 3 would come first and 7 would come last. And in this case, if we wanted to add a new node in here, let's say we wanted to add 4, well, we can't just put it on the end, because if we put it on the end here, then this is no longer a priority queue. And so rather what it would have to do is it would have to insert itself correctly into the priority queue, which it would do right here. So we could do this. We could implement it as a linked list. We could implement it as an array. An array would be a really bad idea because every time you have to insert it in the middle, you'd have to shift a bunch of indexes down, which is a really expensive operation. If we did this as a linked list, you don't have to shift anything because all you're doing is changing links. And if you change links, we can do that in constant time. It's the same amount of lines of code. It does one thing. But heaps allow you to do this a little faster, because the really slow part is if you have a really long list here and it's sorted, and let's say we had a list of 1,000 nodes, and we wanted to insert something that needs to go at the front, and we start looking from the back. Well, now we're looking through 1,000 nodes linearly before we can actually, do something. Or the other way around, I guess, since it goes front to back. If we wanted to put it at the back, we started from the front, we'd have to go through every single node, which is really slow. So that's where heaps come in, but we're not talking about that right now. Okay, let us jump into a queue problem. We'll do one and then open it up for questions and release everyone. Can everyone see the browser here? Just want to make sure I share the right thing.
Yeah.
Okay, great. So we're going to go ahead and go into topics. We'll go ahead and select queues, click begin, and queue. Okay, we'll go ahead and do this one, just because this is not a linked list problem. This is, like I was saying, this is an array implementation of a queue, where they've created a struct for us and we need to enqueue to the struct. So let's go ahead and do this one, just for some variety. All right, I'm going to go ahead and take out this other stuff that we don't need, and we'll copy in our struct definition here, and then we'll also copy in our enqueue definition, and we'll go ahead and write this function. So this queue is implemented as an array. It has two attributes. It has the front and the size. So all of our values are stored in this array. It is a fixed length 20, which means we cannot have more than 20 elements in the array. And front is the index that is the start of our queue, and then size is the very end of our queue. Or not the end of our queue, but it's how many elements are currently in there. So it may not be 20. It might be like 5 elements at a time, in which case the back element would be front plus 5. But we'll deal with that in a second. So they're just telling you that this is called a circular queue because the front does not have to be at the beginning of the array. It can go through the end of the array and then start back at the beginning. So this is where the mod operator will come in. And it gives us our struct definition. And we need to write an enqueue function, which means we're going to put something onto the back of the queue. So if the queue is full, we're going to return 0 and take no other action if size is already 20. If the queue is not full, then we need to enqueue the item to the end of the queue, make any adjustments to our struct, and return 1. And again, it'll give you a little bit of information usually at the end just to resolve any edge cases that it doesn't want you to have to deal with. In this case, it's a hard-coded 20, so we don't need to worry about different sizes of the queue. Okay, so let's go ahead and write this function really quick. So the first thing we probably want to do is check if the queue is full. And we can do that with this queue size is equal to 20. Then we'll return 0. It shouldn't ever be more than 20 because we're not enqueuing anything if it's already full. If we wanted to play it safe, we could do greater than or equal to. I assume that equal to 20 would be perfectly fine for that question. And so that covers if our queue is full. And so now that the queue is not full, we need to figure out what index we need to insert into. So let's go ahead and make this variable just to make things more clear what we're doing here. So this queue front plus this queue size. So if the size is 1, then it'll get us the index directly after the front. If it's 2, it'll get us the index 2 after. Basically the first index that is not in use after the queue ends. And this could be longer than our array is. If our array is of length 5 and front is equal to 3 and size is equal to 4, this array could look like 0, 1, 2, 3, 4. And so our front is right here and our size is 1, 2, 3, 4. So this element is not in play. But in this case, if we just do this queue front plus this queue size, well, it's going to go past the index, the ending index of our array. So we need to make sure that we go ahead and mod this by the full length of our array, which is a fixed value of 20. So if it goes past, we'll reset it 0. And so now we can go ahead and insert. So this queue will get the values and we'll index to the inserts and we'll give it the item. So this went ahead and put it in, but we also need to make sure that we're making the necessary adjustments, which is intentionally vague. We need to figure out what those adjustments are. Our front value does not change, but the size does. The size is now 1 bigger. And so we can do this queue size plus plus. And now we need to make sure we're returning an integer. In this case, we're going to return 1 if this worked successfully. Okay, let's make sure we did everything properly. If the queue is full, we'll return 0 and take no action. So if the size is equal to 20 or greater than or equal to 20, doesn't matter. Then we'll return 0 and take no other action. Otherwise, we need to insert the item to the end of the queue. So we're going to take the front, add the size. So in this case, it would be front plus 1 plus 2 plus 3 plus 4. So we'd be referencing this not in use index. We're going to go ahead and insert the item into that slot, and then we're going to increment size by 1. So now this would be 5. And if this item was 5, then that would go in there. And we return 1. So this looks good to me. Let's go ahead and submit it. I didn't actually start the problem timer. Okay, so we have our condition first, if the size is equal to 20. Otherwise, we're going to get this index. This is really disgusting, so I went ahead and put it in a separate variable. But this Q values that index is equal to item, and then we increment size and return 1. So this is pretty easy. There are certainly some harder questions out there. I think the hardest questions with queues and stacks are usually the trace problems. If you have like code that goes through and uses them and like, pops a bunch of stuff off, puts a bunch of stuff on, that can get really confusing really quick. And so you need to be able to like draw out each step, what the stack or the queue looks like, and then what it is at the end. The coding problems are not usually as bad, but this is just personal observation. It's going to be different for everyone. All right, we are basically at 9 o'clock. We have about 3 minutes left. Thank you everyone for sticking with us. It was great to see so many people engaged with this. Certainly join the Google Developer Student Club Discord. We'll be doing this every week, all the way through the first week of school. I think it'll be just Zane next week. If there are any remaining questions, go ahead and ask them now. We'll stick around for a little bit. But thank you, everyone. Have a good night. Have a good winter break, and we'll see you next week.
Yeah, have a good night, everyone. Last 2 minutes to ask questions.
Yes, I can redrop the Discord invite. I think I put it way at the top, but it's very far gone now. I will try and post announcements for these in all of the different communities. I put out some reminders in the big CS Discord and also on the Night Hacks Discord, which I'll try and do every week, but I'm not promising.
I'll do
All right, so here's the link to the GDSC. Go ahead and join that. That'll be the best place to get the announcements.
Oh my god.
I'm not saying no, but you should definitely not do that. You got this. You already know what's on there. You're well experienced at this point.
No problem.
I believe in you. All right, 1 more minute for questions if there are any. You can unmute, you can type, whatever. And then we'll close the meeting. Thank you. Have a good night.
Okay, looks like no questions.
Looks like no question.
Oh, there we go.
There is a question. Yeah, we don't have access to the GDSC YouTube, but that's where it'll be uploaded. I'll send the recording to Ryan after this. Hopefully it'll be done.
On Shep though. Oh, sorry. Go ahead.
Yeah, it won't be on Shep. It'll be on the GDSC one, probably this weekend, but I don't know when in particular.
If you go to the study tool website, there's links to like the Night Hacks one, the Shep sessions as well, because these have been done before. I did them for Night Hacks and then for Shep, so you can also see those. If you want to move a little quicker than a week by week breakdown, because we're not covering all the topics all at once, you can just go and see them. Just on the different workshops that I've done.
Zane's the foundation exam pro at this point. All right, that is everything. I will go ahead and
Have a good night,
shut
everyone.
this down.